Welcome to today's lesson on exponential and logarithmic equations. We began by talking about exponential form and making the base the same for two numbers. For example, in number 1, we have two numbers, 2 and 32. The desire is to get them both to have a base of 2. Well, 2 is 2 to the power of 1, and 32 can be written as 2 to the power of 5. Looking over at number 3, it's very similar. 8 can be written as 2 cubed, and again 32 is 2 to the power of 5. We're getting a common base of 2 in numbers 1 and 3. In number 4, we can't use the common base of 2 for a number like 9, but we could write 9 as 3 squared and then 27 as 3 cubed. Moving over to number 6, we see the number of 16 and the number 8. We want to go down to the base of 2 again, so this would be 1 over 2 to the power of 4, whereas 8 is 2 cubed. Well, we don't want to have a fraction here, so we're going to write this as 2 to the power of negative 4 and 2 cubed, getting a common base for both of those numbers. 7 has a square root in it, so remember the square root of 2 is 2 to the 1/2 power, so we're going to go down to a base of 2. 1/4 is going to be 1 over 2 squared, which can be rewritten as 2 to the negative 2 power. When you're getting a common base, it's most typical that your base will be a 2 or a 3, maybe a 5, but they need to keep the bases pretty small in all of your examples in your homework or the numbers become exceedingly large. Now we're going to practice a little bit of properties of exponents, and I don't know if you recall from an earlier lesson or not, but anytime we have a power to a power with a parentheses here, I like to put a little dot on the parentheses, which is reminding me that I multiply those exponents. So randomly picking an example, maybe 11, this would be 3 to the power of 2 times the 4x plus 1. 2 times the 4x is 8x, and 2 times the negative 1 is minus 2. So this is 3 to the power of 8x minus 2. Now we're going to be solving in topic 3, solving linear, quadratic, and rational expressions. Remember, quadratic will have something like an x squared term in it, or if your variable is a, it would be a squared. A rational is when you start having fractions. Linear would be x to the power of 1. So when we approach the solving process for a linear, quadratic, and rational equations, they vary in levels of difficulty and in the way we process them. So look at number 4. Let's go ahead and distribute this 3, making this a 6x minus 15, equaling a 5x minus 5. All of your terms are linear, x to the power of 1. So if we want to solve it for x, we would subtract the 5x, making this an x minus 15 equaling a negative 5. And then we would add the 15 to each side, getting a solution of x equaling 20. That's not correct. It would be x equaling 10. Number 17, if I distribute this x, I would get x squared minus 31x, and 2 to the 5th power is 32. I have an x squared term. Once I have an x squared term, I am now a quadratic equation. So to solve a quadratic equation, I need to set this equation equal to 0 by subtracting the 32. Now I would either factor or go to the quadratic formula, but this one factors into an x minus 32 times an x plus 1. We now set each factor equal to 0 and come up with two solutions to our quadratic equation. I'm going to move to number 20 because this is our rational equation. It has a fraction in it. When I work rational equations, I usually like to make it a fraction equal to a fraction, so I rewrite the 4 as 4 over 1. Then I cross multiply. So 5x minus 13 times 1 is just 5x minus 13. And x minus 2 times 4 would be 4x minus 8. Now to solve, I would go ahead and move the x to the left side by subtracting the 4x, leaving an x minus 13 equaling a negative 8. And then I would add 13 to each side. Now once I get the result, before I put it in a box confirming it is my answer, I want to make sure that if I plug this 5 into the denominator of the original fraction, I do not result in a 0 as a denominator because that would make the fraction undefined. A value of 5 will make that denominator a 5 minus 2 or a positive 3, which means that it's safe, that I did not cause an undefined situation when solving a rational equation. Now I'm going to move to the next page, and I'm going to move down a little bit into the connection to college algebra. So in this connection, we're continuing to solve the equation. We're going to go back and use our original skill of common bases on number 1. We have a base of 5, and 625 can also be written with a base of 5. So on number 1, I have 5 to the power of 2d minus 4 equaling 5 to the power of 4. Now that I have common bases, there is a property that permits me to set the exponents equal and kind of dropping the base. So I have just a 2d minus 4 equaling 4. Now I solve this very quickly by adding 4 to each side and dividing by 2, and I have a solution. This is why we were practicing common bases, because it works out beautifully for these solving situations. Number 3 is like a quadratic equation. It's not e to the x, but rather it is e to the 2x, which puts it in more of a quadratic form. So in this situation, my goal is to hopefully be able to factor, and this factors into an e to the x times e to the x, and the two numbers that multiply to be a negative 32 and add to be a negative 4 would be 8 and 4, with the 8 being negative and the 4 being positive. So once I have it factored, I set each factor equal to 0. And go ahead and solve for e to the x. Now, e to the x cannot equal a negative number. If you remember the graph of e to the x, it cannot be under the x-axis. So this is not going to present any solutions. But the e to the x equaling 8 will present a solution. We need to solve for x. The answer is x equaling a number. So the way we solve this is by taking the natural log of each side, and then remembering the natural log of e to the x is x. So our solution is x equaling the natural log of 8. Now let's look at number 5. It's a little different. Number 5, my equation is e to the 2x minus 49 equaling 0. Having an e to the 2x power means again it is quadratic. So this is like a difference of perfect squares, in which this is e to the x plus 7 times e to the x minus 7 equaling 0. Just as in number 3, I will set each of these factors equal to 0. And I will get e to the x equaling to a negative 7, which we've already discussed that cannot present a solution, and e to the x equaling a positive 7. Just as in number 3, my answer is supposed to be x equaling a number. So I will take the natural log of each side of this equation so that I get my result that x equals the natural log of 7. These are exponential equations that I just solved. Numbers 1 through 5 are exponential equations. There is no logarithm in the equation. So as I move down to the next set, notice in part 6, these all have logarithms in them. So these are logarithmic equations. Anytime you're given a logarithmic equation to solve, you want to take note from the very beginning whether all terms are logarithms or not. Look at part B. The first term is a logarithm, the second term is a logarithm, and the third term is a logarithm. So yes, all terms are logarithms. If you look in part 7 on part 7a, your first term is a logarithm, but your second and third terms are not. So 7a, not all terms are logarithms. If they're all logarithms, you solve them differently than when they are not all logarithms. So let's solve and learn the process for solving a logarithmic equation in which all terms are logarithms. When all terms are logarithms, you want to make this so you have a log equaling another log, whatever the argument is. Well, my left side of my equation is addition, so I can rewrite this as one logarithm of log of x times x plus 15, making one logarithm now on each side of the equation. Once I get one logarithm on each side of the equation, and they both have the same base, in this case of 10, I can set the arguments of the logarithms equal and drop the logarithm. Now I just solve a quadratic equation. I know this is quadratic because I can see in its head that when I multiply the x times the x, I'm going to get an x squared. To solve a quadratic, I know I need to set this equal to 0 by subtracting the 100. Then I hope it will factor. And if it won't factor, I would have to go to the quadratic formula. But this one factors into a positive 20 and a negative 5. I now set each factor equal to 0 to get two solutions. Now, before I square off my solution as a definite answer, I must remember that the argument of the logarithm must always be a positive value. So if I had a negative 20 and I tried to plug it into the first term here, my argument of my logarithm is not positive. That means this is not a solution. Now if I plugged 5 into any of these logarithms in this original equation, the argument of the logarithm would still be a positive value, and therefore x equaling 5 is a good solution. Moving down to part 7, where not all terms are logarithms, I will use a different process for solving. This process for solving is to get one logarithm equal to a number. So here's my one logarithm. I want the 10 to move to the other side, so I have one logarithm on the left side of this equation equal to a number. Once I get one logarithm equal to a number, then I can come in here and change it from a logarithmic equation to an exponential equation. So converting this logarithm to exponential would be 3 squared equaling 5q minus 6. This is now a linear solving situation. And remember, your goal is what is the value for the variable, so the solution is q equals a number. If I add 6 to each side of this equation and then divide by 5, I get a q value, or a solution of 3. Before I square this off as my answer, I need to be really careful and look back up at my original equation to make sure that that number 3 does not make that highlighted argument a negative value. If I were to put 3 in for this q, this would say 15 minus 6, which is a positive 9. That is a positive number, so this value of 3 as a solution is a good solution. So remember, in number 6 and 7, these are logarithmic equations. You have two ways of answering. One is if all terms are logarithms, get one logarithm equal to one logarithm, drop the logs, and solve. Versus if not all terms are logarithms, get one logarithm equal to a number, and then convert it to an exponential equation rather than a logarithmic equation to then solve. I hope this recording was helpful for you, and that you'll be able to flow more naturally through the for the uses of logarithms and exponential equations.